Hi everyone, and welcome to the webinar on soil structure interaction modeling for piled and non-piled solutions using MIDAS GTS NX. My name is Mehdi Ebadi. I'm an Associate Director at AGL Consulting in Dublin, Ireland. A bit of my background, I hold a PhD in geotechnical engineering, civil engineering. My master's was also in geotechnical engineering, and my bachelor's was civil engineering. Uh, I've been working with finite element or finite difference simulation software programs since 2007, I can say, geotechnical ones, and particularly this MIDAS geotechnical software uh, from around, I think, 2008 or 9 uh, uh, in Shiraz University at the time. So in this webinar, we are going to actually, from some aspects, briefly discuss the key points or key aspects of the soil structure interaction. Obviously, we can't go in depth. That's a comprehensive topic to be discussed, but we try to actually give useful and practical information from three case studies that we have delivered in the recent years in AGL Consulting. So, okay, in this webinar, we start with an introduction to the soil structure interaction. Actually, we go through the importance of SSI on the projects, how it influences the geotechnical side of the design, the structural side of the design, and as the kind of final step for verification of a proposed design. Then we uh, briefly discuss the capabilities required for a proper SSI using finite element method, and that we have found these required capabilities in MIDAS GTS NX for our projects. So from the projects that we've done recently in different countries in AGL Consulting, we've selected three representative projects, and these projects will be briefly discussed. We will briefly go through the challenges and the actually potentials of MIDAS GTS NX for solving these problems, and then we'll go to conclusion. The case studies, actually the first one is a piled foundation for a residential building in Ireland. The second one is actually it's a very big project. It's a semiconductor facility in a Western European country. And the last one is, um, as we usually call it, machine foundation. It's Siemens gas turbines foundation. So it's for a power plant, and as we do have NDA contracts with the clients, I cannot provide a specific detail about the locations, client, and such, while this doesn't influence the technical aspect of the presentation. So we'll proceed with the information that we can share with you. So Okay, so the soil structure interaction is, as we all know, a coupled response between the soil and the structure system. And this is under the loads that are applied by the structure to the soil, and there is a stress redistribution in the soil, which on the other side influences the structure, both from the aspect of sufficiency of the strength of the soil to resist against the forces by the structure, or the displacements that occur in the soil, which cause deformations in the structure, and that deformation uh, in general will result in forces and moments in the structure, which has to be within, or let's say safely within, the capacity of the structure. So these two general aspects are the main reasons that we follow the soil structure interaction analysis. When we do any of these kind of analyses, we have to do this in parallel with the analytical or empirical, semi-empirical methods. And there are many reasons for that. So, for example, for this schematic, let's say, foundation that is currently on the screen, as you can see, there is a mechanism of load transfer. Usually in the lab, uh, researchers in years of experience have analyzed them, have captured their behavior in field under different loading conditions, and have obtained dependable formulas and methods for calculating both the capacity, let's say the ultimate capacity, and the load deformation behavior. So we will have methods to kind of estimate. In some cases it's not that accurate, but we will have some numbers for comparison. And this should be always kept beside what we do in a software program. So doing finite element, finite difference, any type of simulation, that's great. That's what we do for obtaining highest accuracy of results. But on the other side, we always need to have some kind of analytical or empirical set of calculations and results to make sure what we've done in a software program, in simple terms, makes sense. For a piled foundation, the soil structure interaction analysis is usually much more complicated compared to a normal foundation. And the reason for that is the load transfer mechanism, which, for a normal foundation, it's just underside of the foundation. Either it's, a single level or has a few levels up or down. But for a piled foundation, even assuming that it's under pure vertical load, the load that is applied from the superstructure is then transferred to the top of the piles, and then from the piles to the soil, depending on the design and resistance provided by the side resistance or the tip resistance, or both, on this pile. And the thing is that the area between the piles also contributes as a kind of multi-layer interaction area, because, for example, this area is influenced by, in general, by the adjacent or surrounding piles. So this was only an axial load. When it becomes a more complicated or more realistic, let's say, case where we have lateral loads, where we have torsions, moments, those kind of things, then analyzing this will not be as easy as, for example, a pure vertical loading. And the spacing, diameter of the pile, and behavior of the soil, those things are of much more importance in such cases. So normal parameters that we usually consider, for example, for deformation, like stiffness and these kind of things, these should be captured in much more advanced models, which we'll discuss later. But just referring to different levels of complexity, this one is obviously much more complicated compared to normal foundations that are generally for big projects. They're usually, when we have considerable pressures, we usually use raft foundations. But anyways, that's a key point to be considered when we are going to start a project and an analysis. Okay, so assuming that you want to do a soil structure interaction analysis for a project, the most important step for doing an SSI analysis is the first step, which is understanding the requirements of the project. For example, we have projects in which the structural team asks us to provide forces and moments so that they would be able to do the structural design and calculate the required reinforcement for the structure. This is one major category. The other major category is that they ask us to do analysis for obtaining the settlements and deformations of the structure and the angular distortions, and then we provide those values so that they check those values against the tolerable thresholds of their structure. In some cases, which are usually for industrial uh, projects, we have predefined limits that are generally governed by the equipment that is supported by the foundation. So these two things are two examples of many different cases that could happen, and but I think they are the most common ones. But you need to know in advance which one you are asked for, because the tool that you need to use for each of these is different. For example, if you're asked to do an analysis and provide forces and moments, you need to use gouging shell if you are using a bulk element. And if it's only settlements and angular distortions, then you don't need to do gouging shell. So these things should be known and understood in advance. The next step is to identify the key elements of your model, and the surrounding structures and things that are on the site that you want to do the modeling. So, well, we can't model the whole city or whole neighborhood to make sure that everything is accurate. And usually, even if we have, let's say, for argument's sake, we have time and energy and everything to do such a thing, usually the results do not make any difference in engineering practice. So we need to select the most efficient way of modeling the things. Usually the way we do it is that for the buildings we select the first one or two levels if it's high rise to consider the rigidity of the structure to some level, the superstructure, I mean, in the analysis. Anyways, we have many different cases that can happen, and for each one, you need to select the important elements, the key elements, and consider them in the model. We'll try to actually for the case study projects, we'll try to refer to these ones very briefly and uh, provide information that would be useful for the users. So for the geometry and the domain of the project, that absolutely is very important. If it's too tight, then you're confining the compressible layers, which is generally soil and rock. And the results that you get are usually lower than what happens in reality. And on the other side, if you have a model that your limits are too wide, that's adding unnecessary elements to your model, which you'll pay for by spending more time and energy. And on the other side, unfortunately, less accuracy in general, because your elements cannot be as small as you need. Otherwise, the calculation time will exponentially increase. So that needs to be in balance. We have different, let's say, cases. For static loads, usually we try not to have something, let's say, less than 5b, 5 times the width of the, or any dimension of the element that we want to model. And when it goes to dynamic, we go to at least 10b. But that's not an absolute value. That's just a kind of a guide, uh, let's say, estimation for considering as a starting point. Then we go to material models. So if it's a very simple analysis, or if you don't expect any complicated mechanism in terms of load transfer, in terms of yielding, or in terms of interaction between different elements. For example, if you have a foundation that is sitting on a layer or two layers of soil over rock, that the stratigraphy is horizontal, there is no complexity in that, and you are just analyzing this against levels of pressure that you don't expect yielding or such. Well, if you want to use simple models, even uh, linear elastic would give you some levels of good results for these projects. They're quicker, and we have a separate uh, type of or category of analysis just for linear analysis in MIDAS, which is really handy. If you want to go one level deeper, more column, as we all know, is useful. If you want to go more in depth, then you should go to models like hardening soil model, hardening soil small strain, and we can go deeper by selecting case appropriate or case specific uh, soil models depending on the requirements of each actually model and the materials that are involved in that. That's another category we just briefly refer to it. Interface is an important element. We shouldn't use the interface elements in every project for every interface between a structure and the soil. My experience, at least supported by different field tests, say that, for example, for cast in place foundations, it's better to be cautious in using interface elements in finite element modeling. We'll discuss that later, but just wanted to, as a high level comment, I would say don't use this for every interface between a structure and the soil. It looks nice, but sometimes the results that you get are not that realistic. It depends on the method of construction. That's a general note. So then we go to boundary conditions. So we have automatic boundary condition uh, in MIDAS, and we can actually define that manually. So if your boundaries are far enough from the model, it doesn't matter if you make your side, assuming that it's static, if you use fully fixed or rollers for the side boundaries. But if you are not sure that your boundaries are far enough or not, absolutely use rollers for the side boundaries. That's, again, general note for that. So then you have the type of loading and type of analysis. MIDAS is really good in terms of loading and the inputs and the way you can define the loading. So either it's static or dynamic. For dynamic, you have time history, different types of inputs. That's a big category to discuss, and would require, I think, 10 webinars on that exclusively. But for static ones, you can, as you know, apply point load, line loads, uh, and gravity loads, area loads, those kind of things. That's important to know which loads to consider and to apply the loads at the stages that they really happen in practice. Then we go to the type of analysis, which in general, for many projects, we only use nonlinear static analysis because we are talking about the Europe, and in the Europe, well, regardless of some countries, the earthquake is not the governing parameter. So usually the type of analysis that is more common is just the static analysis. Then we go to outputs, and in the outputs we need to check our results against what we have in parallel obtained from our hand calcs and from uh, other methods that are, outlined in codes and textbooks and such, so that we make sure that the numbers that we are getting are correct. There are different sources of error that can happen in software programs. Uh, we do not want to uh, discuss those things, but in general, you may realize, okay, I've forgotten to, for example, use correct values. I've forgotten to apply uh, or input a number for stiffness. So many things can happen. You should know what numbers in general or what range of numbers you should expect. And the important thing is that you are the designer. MIDAS is a tool. So you can't blame a program for something that you have no idea on the orders. So if you find that the numbers are far from what you get using hand calcs, or it should be within same order of magnitude, while you may say, okay, there's no method for hand calcs for this. Well, make assumptions, get values. It shouldn't be like 100 times more or less. Let's say 50%, 60% max, more or less, would be reasonable. Anyways, so soil structure interaction is just one part of a set of sequences that we follow for a project, starting from site investigation and characterization. Then it's the geotechnical analysis, including soil structure interaction analysis. Then it will be the design and assessment, so using the numbers that we get from that. Then it's construction, as you know, monitoring and instrumentations, and then the operation and the a model that we do in soil structure interaction, or in general in finite element modeling, includes micro level, which is like particle size level, then element scale level, which the mesh size would be the governing parameter for that. Then foundation scale, which is the arrangement and what has been designed or will be optimized by our analysis. Then the structure, which will be the whole thing between the structure, what we are modeling, and the soil. And then at a higher level, interaction between the structures in an area, like influence of construction of a building on a tunnel or vice versa. Okay, so the first case study project that we review in this webinar is a residential development in Ireland. It was a piled building and between 8 to 24 stories. The areas that we want to discuss in this case study are core 1 and core 2 of this building. Core 1 is this part, which was 1.5 meters thick, and it was supported by 38 number 600 millimeter diameter piles. And this part, core 2, was supported by 1.8 meter thick and 67 number 900 millimeter diameter piles. So in total, it was supported by 105 number piles. What we had in this project was two test results, two preliminary test results in the area. And those test results were done on two piles. So one of the piles was a screw-saw soil displacement pile, which was 430 to 600 millimeter diameter pile, and the other one was a 900 millimeter CFA pile. So the first one, the 600 mil one, let's say, was 18 meters long, and the CFA one was 22.3 meters long. The load applied to the 600 mil pile was 4,250 kilonewtons up to this load, and it was a cyclic loading unloading. As you can see here, this is for 600 mil. The dark blue dots show the test results, and the plot uh, that I'm now referring to, this is the test results for the 900 millimeter diameter CFA pile, which had the maximum loading of up to 7,500 kilonewtons. So these two piles, well, as shown in the previous slide, were in the area that were just beside each other. So, and they were going to be used by different methods of installation and construction. As I said, one of them is screw saw soil displacement pile, and the other one is the normal CFA pile. So we first had to get to a point that we make sure we can capture the behavior of each pile in the soil, which is a soil structure interaction. In this case, the structure is a single pile under loading and unloading. So what parameters we could work with? In MIDAS, we have tools for actually calibrating the models using the test results. But in this example, I don't want to go through those things. This is the method that we used and we found suitable for our needs. And for our model, we used bulk elements. So we didn't use line elements or embedded beam or anything like that. We used bulk elements, so like a body of concrete. And the parameters that we could work with were generally the interface parameters and the soil model parameters that we could work with and calibrate our parameters with them. So we manage those calibrations, and the orange points that you can see here, which are pretty good actually following or matching the test results, are the results from MIDAS. And the model is shown here. So we used a polar system, triangular in plane elements, and we modeled each of these piles. This is for one of the models. And based on the stratigraphy that we had in that project, we set up the model and got the results. Actually, the stratigraphy was generally alluvium over sands and gravels, and then over limestone. So when we got to a point that we could capture the behavior of a single pile in the model, then we got the confidence that we would be able to do the same for the whole structure. Note that from at least our experience with different software programs that we currently have in use in our company AGL, we found MIDAS really good in modeling bulk elements for piles, because in some tools, unfortunately, you cannot use bulk elements. If you use them, you'll encounter endless errors, which will be actually very frustrating. But the importance of using bulk elements is that in reality, a pile is a bulk element buried in the soil. It's not a line, it's not anything. I know using embedded beam, we get very good results. I'm not going to argue that, but what I'm saying is when we want to model something in a way that we get the most accurate results, the bulk elements are for that. So this is not the easiest way to do it, but this is I can say in terms of accuracy, the best way to do it. And that's what we did in this project. So as you can see on the right in this area, so this is the model that we had, and the two cores of the foundation that we've modeled with the stratigraphy. We added the shear walls and columns of the basement floor so that we would have the rigidity of those elements in our analysis and the results. As you can see in this screenshot from MIDAS, we have the foundations as bulk elements. Normally, not only MIDAS, in general, piles are modeled as embedded beams, which are essentially lines, but and they are the quickest, most efficient way of modeling this. But as I said, when you have time and when you have the chance to provide the most accurate set of results, then MIDAS, we found, is the tool or one of the best tools for doing this. And using bulk elements is the best way of doing this that we could use. So then there are different ways to extract the loads per pile for these, which we did. And for settlements, you can simply, like what I did here, you can simply extract the settlements of the piles, which were in this case generally less than 10 mil or up to 10 millimeters. The next project that I would like to discuss is a semiconductor manufacturing facility in a Western European country. This project was actually a high profile project as well, which was reportedly valued at approximately, I don't know, more than 7 billion, and included two main buildings. One of them was the fabrication building, or they called it fab, and the other one was a central utility building, which was called COB or COP building. So we were asked to do an analysis and uh, calculate or obtain the settlements of this of the foundations for this project, and then the structural team were going to check them against the tolerable limits of the superstructure. So the foundation of this building, which I start with the bigger one, or I focus on the bigger one, which was the fab or fabrication building. It was an integral rectangular slab with 2 levels, and the surrounding part of the foundation was at lower level and the middle part was at higher level. The thing was that in this case, or in this project, we had, because as you can see in terms of the dimensions, this foundation was 226.5 meters long in 196 meters wide. And the model that we have used for this, because the loads were not compared to the dimensions, were not that big. So we did sensitivity analysis for that as a high level thing, not for a detailed model. So the dimensions of the model that we have considered were 600 meters in 400 meters. So it was quite big model in terms of comparable real sizes. And the stratigraphy in the area included different layers of syenite rock. And as you can see, this is from another report provided by AGL reviewing the stratigraphy of the area under the foundations. So we have different layers, and this hatched area here is the area that was of poor quality, highly weathered soil that was going to be excavated and replaced by a suitable material. So the model, as you know, in MIDAS, we have a bedding plane as a tool that we use for obtaining a stratigraphy. And the bedding plane tool works with borehole options that we define in different locations. When we have several boreholes, in this case, as you can see, in 400 in 600 meter area, you have several, and in plan you can see, then the program interpolates each layer based on the immediately adjacent boreholes or rotary core holes, or in terms of the program definitions, the layers that we define. You may not be able to capture the exact same stratigraphy as what the geologists or the geotechnical team provide to you. So you may need to use items like extrude, like cut, like merge, those kind of things, like fuse in MIDAS to be able to replicate the same stratigraphy that you have obtained in your geotechnical analysis of the stratigraphy or have been provided to you. This is very important because sometimes you'll see that the layers that you are getting from the model may not fully capture what you are asking for. And that's because the program uses interpolations for obtaining a surface that would get past the bedding plane of each layer in different SI locations. So that was actually one of the challenges, because it was something that we initially couldn't capture. Same pattern as you can see here this is for this higher level foundation. So the foundation, as you can see, had both large actually dimensions and many different details from both the aspects of uh, lift bits and those kind of things, and columns, and the different thicknesses of the foundation, even the geometry of the foundation. It was trapezoidal and kind of corrugated on the underside. As you can see here, this is the underside, and this is looking from top. As you can see, we've captured all the details in the model that were relevant. If we want to model, as we discussed, we need to first make sure that the elements that we are considering are the elements that are relevant. For example, a metal staircase is not something that would influence this big foundation on the soil. So we used a hybrid mesh for this, and as you can see, we have a combination of triangular and polygon elements, or as I said, a hybrid mesh. And the mesh is refined in the areas where we have columns and loads, and has larger size in the areas which are under generally area or line loads, which, as we know, is what we normally do in finite element modeling for getting more accurate results in the areas of interest, in this case, the column forces. So one of the things that I like about MIDAS is the potential in uh, modeling loads. In this case, the loads that were provided to us, for example, the area loads, had overlap, which, in MIDAS, you can apply different loads to a single node or a single point if we start from scratch, which will be then by applying suitable methods, you'll get that in your mesh. But anyways, I show you this slide, which only shows the point loads that have been considered from one load case in this model. So you can have different load cases. In each load case, you can apply loads to different nodes, and then by having a combination of those load cases, you'll have different combos for different conditions. Either it's static, or a combined of static and pseudostatic loads that you considered in your analysis. So in this model, we had point loads, we had line loads, and we had area loads. This is just an example of the loads applied in this model. So what did we get? We did an analysis, and the upper layers were, as we discussed, were less, or let's say, highly weathered, and the deeper we went, we got to fresh or nearly fresh rock layers. So we had higher settlements on the upper side of the foundation with the pattern that you can see. And the way we wanted uh, these results to be communicated to the structural team was to have them both in terms of settlements and in terms of angular distortions. So we defined lines on this foundation on at representative sections, and on each line we extracted the settlements of the foundation. As you can see, these are all within MIDAS. As we can see, we got the profile of settlements. So whether this profile is within the capacity of the structure or not is something that the structural team should decide. But uh, the input is required to be provided by a geotechnical team through a geotechnical analysis, which is what we are currently discussing. Then we extracted the results and plotted them in Excel. So it's the same results, just the numbers in Excel. We wanted plots that we can work with the values, for example, calculate angular distortions, define changes or such, and that's exactly what we did. So we defined lines on the upper side of the foundation, which was showing higher settlements, and we extracted the settlements for these areas. Then accordingly, we calculated the angular distortions for the foundations. And the results showed that except a few localized areas which we communicated to the structural team, in general, the angular distortions were less than 0.006%, which were really low and within the tolerable capacity of the structure. The last case study that I would like to discuss is the Siemens gas turbines for a power plant in Ireland. And as you can see, this is the layout, and this shows the three number gas turbines, which are these equipments on foundations that I will show in the next slides. Okay, the turbines will be supported by this foundation on the left. This figure on the left is from the drawings provided to us originally by Siemens, and the other parts are light utility elements that are to be supported at the sides of the main foundation. So there is a main foundation which you can see we have modeled on the right. This is what we've modeled from this on the right side, and uh, the other elements are not critical because they were not under heavy or dynamic loads. So as you can see, we've just done this using simple extrude, fuse, cut functions of MIDAS without a luxury of having the model file as an input, which is an option in MIDAS, but we didn't have such an input. Anyways, okay, as you can see on the right side, this is the model that we set up for each of these foundations for the analysis. Okay, what were we asked for? We had a Siemens specification, and in the Siemens specification, there were different items to be checked. One of them was the load deformation behavior under different load combinations, which were live loads as a category, accidental loads like blade loss and those kind of loads as another category. And the last one was a dynamic analysis to make sure that resonance and associated settlements or deformations would not occur under the applied loads based on the properties of the foundation and the soil and the interaction between these two. So this is the model in general that we did based on the exact design. And the one on the left side is just general shading of the deformations, which in this case, the deformations were generally low, I mean, less than 2-3 mil. So we analyzed 76 load combinations for the accidental loads. And it was quite easy. We have the loads and just we define the combinations as a table in MIDAS. So straightforward and very easy, while this option unfortunately is not available in every software program. Then the deformations obtained by the analysis in MIDAS enabled us to calculate the angular distortion of the foundation and then to check that against the criteria specified in the Siemens specifications for these foundations, which should be within the tolerable limits for the equipment. So we had different load combinations for each load combinations. For each load combination, we got settlements. There were criteria to check against. Angular distortion, we did the same. We had, for example, for this case, for accidental loads, 76 number accidental load combinations. We did the settlement analysis, this angular distortion calculations, both checked. Okay, next step. So the next step was to do an analysis for calculating the first 20 natural frequencies of the system under the applied load. This is as per DIN 4024-1 and is also outlined in the Siemens specifications. As you can see, we modeled it in this time the three turbines, which were 42 meters away from each other. And these are the foundations. We consider the weight of the or the mass of the elements supported, and we did a modal analysis, which is just one category of analyzes in MIDAS. It's really handy and very easy to be used if you know what to actually use for doing this. Otherwise, you need to do, I think, days, if not weeks, of calculations for obtaining natural frequencies of a complicated model like this. Anyways, on the left, you can see a comparison between one of the machine frequencies, in this case, the dominant frequency of turbine, which was 110 hertz, and these 20 points that you can see on the left are the first 20 natural frequencies of the system, which are much lower than the turbine frequency, which gives us the confidence that there is no risk for resonance or such. When we refer to the codes, we'll see that we should be, depending on the code, between 20 to 25% more or less uh, below or above the natural frequency of the system. In this case, we are by far at a better position for confirming that the system is in safe condition. So this is the dynamic part of the analysis. Note that although for such a case we have the option in MIDAS to apply like sinusoidal load and do time history analysis, we didn't find such an analysis useful for the needs of the project, because when you know that the settlements are well within the capacity, your system is not at risk of resonance or such, then doing time history analysis is not something that would add much to your findings from this project. So when you see an option in a program, that's great, but we don't need to use those options for every project. You should, as I said, see the needs of a project and then use the options accordingly. Okay, summarizing what we discussed, we as we said, we have general principles of a model, which is understanding a problem, selecting the key elements and including them in the model, selecting an appropriate soil model based on our needs. It can be either linear elastic, more Coulomb, or going to advanced models like HS small plus dynamic properties. Meshing, that's very important to know where to refine the mesh and where not to. Generally, the mesh should be refined in the areas of interest, at least. For non-piled foundations, we should make sure that we are using the correct stiffness and details as per what is going to be used in the structural analysis. For piled foundations, we can either use embedded beam or solid elements. For quicker, normal, general use models, embedded beam, if you want very accurate results, it needs calibration. The calibration is different from normal calibration in MIDAS. Then you should go to solid elements. So you need to check everything that is, uh, a part of the results of your uh, analysis, and at each stage that you're uh, actually inputting the information, you need to check to make sure that the information that you're adding is reliable and uh, reasonable. Okay, then you do a soil structure interaction. If your model is a model that you have imported elements or the structure from other software programs of MIDAS, so you have the structure, you have the soil, then perfect. You'll have a full model with everything. It will be really accurate. Otherwise, you use the information that you have, you use the elements and do your static or dynamic analysis. Make sure that in your staging sequences, you are not either uh, oversimplifying the project, or you are considering too many details. Obviously, adding too many details will not be something that would in most cases cause technical problems. It will uh, cost you time and energy. But jumping from a stage 1 to a stage 10 will reduce your accuracy in terms of modeling, for example, for an excavation and a staged excavation. And for interface elements, usually when you find that properties of the soil at the interface in real practical condition, assuming that you're following the design, is lower than the soil media. So then you need to use the interface. Otherwise, I found using the interface, even with an interface factor of 1, something that may, in some cases, depending on the case, it's not a general prescriptive comment, but you should be cautious, let's say, in using interface elements. Groundwater and seepage. You have the option to use coupled analysis of seepage, dynamic, consolidation, everything in MIDAS. But again, you should make sure that the elements that you're bringing in to be considered are the elements that would influence the design within the engineering accuracy. I mean, if you have an element that adding it would change the settlements by an order of, let's say, uh, a fraction of a millimeter, but you need to spend 2 days in adding that. Okay, there's no point considering this. And boundary conditions, depending on the model, dynamic or static, you should select appropriate boundary conditions for your model. And for validation and sanity checks, you should make sure that your results are comparable to what you do by hand calcs. And, if there are reactions, you can check them against the actions to make sure, they are roughly within 5% more or less accuracy compared to your actions. In terms of stages, we usually suggest doing a preliminary model just to have some initial rough estimations of what you should expect from a model. I suggest using a linear elastic analysis for these things. Then you go to a refined static. If you want to actually get more accurate, you should do a detailed soil structure interaction with all the relevant elements. And if it is a model that is under dynamic or seismic loads, then those loads need to be added and you get your final soil structure interaction results and deformations, forces, moments, everything for your structural design. In brief, as we discussed, you should never rely on software only. You should have your own engineering judgment. It's better to do sensitivity analysis to make sure that the inputs that you are considering are reasonable. Sometimes you find that by changing some parameters, mainly in more advanced models, not models like more Coulomb, starting from hardening soil model or Cancale or those levels of models. If you change one parameter slightly, that will have big impacts on your results. So that sensitivity analysis will help you at least in that aspect. Then all your assumptions, everything that you use should be documented. You compare at least a more Coulomb model or a linear elastic model with your results. The results shouldn't be that much different. I mean, not an order of magnitude that is unreasonable. And then, if possible, you validate what you've done with instrumentation and field results. Hopefully, thank you very much, everyone. And if you have any questions, you can be in contact with MIDAS or contact me on the email provided. Thank you.